All right. Couple of things to start. Number one, last time when we left was our review day, and you guys made your equation sheets and turned them in for the test. I only got 3 of them from you guys because many of you were like, "Oh yeah, I'll turn it in later, or turn it in tomorrow or something," and then either you didn't turn it in later or tomorrow didn't happen. I think one person, was it Grace, emailed me theirs. But if you have yours, I'd still take it if you wanted to. Yeah, sure. But if you have one and you want to turn that in here, that would be good. If you're like, "Oh, fiddlesticks, I didn't do that. I forgot to do that." You want to give it to me at the end of class or like later today, that would be okay still. But like, don't forget again would be what I would say. Since it seems like some of us forgot the first time. In particular, like for this test, the calculator parts are really critical, that you're able to do the stuff on the calculator and like generate a regression equation, use the regression equation, get R values and all that kind of jazz. So if you, at minimum, I would think you'd want to have like the steps to do that on your calculator on there. You know, that's just me. But, you know, like, if you wanted to take advantage of that, let's try to make sure we kind of get that taken care of here today. Those of you that turned one in, do you want to hear who turned them in? So you're like, "Hey, did I do that or not?" I can tell you if you don't care, and you're like, "Yo, I remember, it's fine."
Mine's in there, right?
Yes. Yeah, I have Aaron, Shanna, Ellie, and then now Grace. So are the people who I have sheets from. Okay. So again, if you wanted to do that and turn it in, like at the end of at the end of class or later today or whatever, that's fine. But try to make sure to remember to do that. You guys remember what happens on Wednesday? That's going to be our test day for Chapter 12. So Chapter 12's test is scheduled for Wednesday. That's why we're turning in the note sheet. Just as a reminder here, last time we talked about the test format. This is on the 217 notes. So you'll have one question where you have to make 2 different models for a data set and decide which one is better and use that better one to make a prediction. So that's all on the calculator, right? You're just doing the regression equations on the calculator and picking the one with the better R squared value and then using that to plug the value in to get a number back. You guys get that? 2 questions where you identify the degree and leading coefficient of polynomials, just using a definition of that. So those are polynomials. You don't have to decide whether it's a polynomial or not. Okay. 2 questions where we ask you to write a linear function. For example, like those numbers 5 and 6 from the problem set. So that's where we gave you that f of notation. But really you can think about those as just x's and y's and use a regression equation to create your best fit line if you'd like. Everybody's okay with that? You kind of remember that? One question where I ask you to make a power model from a data set and then use that to make a prediction. Again, 100% calculator doing that. There's really no work to show, right? One question where you look at some scatter plots and decide which model is best. Again, no work to show there. You're just saying, "Oh, that looks like a parabola, so that should be quadratic," or "Oh, that looks like a straight line, that should be linear," or "Oh, that looks like a doodly-doo, so it should be cubic," or whatever. And I'll tell you the models you have to choose from in the question. So it'll just basically be like, okay, like this one should be, I have like these 5 choices. So this one is this one or this one is that one. So I tell you the regressions you have to choose from or the type of models that you have to choose from. And then one question where I ask you about the reasons a prediction might be unreliable. So you guys remember the reasons that a prediction could be unreliable? So there were several that we had talked about in class. It's been a while now. So one of them is when we're doing extrapolation, right? If you're picking an x value that's outside of the range of data that you used, that can give you a bad prediction. Another might be you use the wrong model, like your R value or R squared value is pretty bad. So you're using like a model that's inappropriate to the data set. So if your model doesn't fit your data, you're probably not going to get a very good prediction. And then the other reason might be like somehow your data set is biased in a way, right? We saw that when we talked about like predicting the heights of people. Like if you picked, like if your data set was from like NBA players and then you use that data to predict heights of normal people, probably wouldn't be very good, right? You have your data is biased in some way, right? Because you picked or you sampled from like a very specific subset. Leo?
Can you repeat those things again? Like
Yeah.
all things that make it wrong.
Yeah, so like the first reason was extrapolation. And then like the second reason would be like an inappropriate model, like your R or R squared values were bad. And the third reason would be like a biased data set. Is that cool? I don't want to go and re-elaborate on all those because it sounded like you were just taking notes, and I thought that just like the main idea would be enough to where you'd remember it. So I didn't like super elaborate. You cool though? We're cool?
Yeah.
Totally cool. Very good. All right. So we feel okay about the test format, what should be expected to do. Again, most of this is calculator, so you really got to be proficient on using your calculator to get these regression models and stuff out of there. Most of the questions are going to require that, and there's really no way to fake it, right? Like you got to be able to generate the model with the calculator, so you do definitely need to know how to do that part. So I would make sure that I've practiced that, and if I'm making a note sheet, that those kind of directions are on my note sheet. You know what I mean? Any other questions about Chapter 12 stuff before I change gears here a little bit? Okay. Great. Again, this test format thing that I'm looking at is from the last set of notes we had before break. Given that we have a test next class for Chapter 12, I didn't want to do the test today because woof, right? Like you come back from break and like walk into the building and like, here's a test. And it's a math test to boot. Woof-a-roonies, right? Like that's kind of a, Mr. Kulik, why are you doing this to me kind of thing. So we're going to instead just start Chapter 13 here a little bit. And we'll do that for the rest of today so that we aren't like, feel like we're cramming a test down our throats as soon as we walk in the building. But we still got to do something, right? Everybody feel okay with that plan? All right. And I won't do like the entire class. If it gets, much past like 8:30 or so, somebody holler at me so that we stop because the B class still has to do the homework quiz that you guys did before the break, so I got to make sure I leave enough time to do that tomorrow without like getting the two classes like wildly off. You know what I mean? All right. So in chapter 13, we're going to be talking more about polynomials. And we talked about polynomials briefly at the start of chapter 12. So when talking about the graphs of polynomials, there's two features that we're often quite interested in. So the first type of feature are the extrema. Those are the high and or low points in a graph. Now, there's really four types of extrema, or there's four ways to classify extrema. So you have high points, which are called maxima. That's just the plural for maximum. And there's low points, which are called minima. That's just the plural for the word minimum. And then we want a way to differentiate a situation like this. So let's say I have a graph that looks like this. So I have one maximum here, a second maximum here, and then I have a minimum there. Everybody kind of agree with that? So if I look at those two maxima, one of them is higher than the other, right? Everybody agree with that? And really, one of them, the one on the left there, is the highest overall point on the graph. Correct? So when we talk about the overall highest point on the graph, if one exists, we call it a global maximum. Now, the other maximum that I have here is still a maximum, but it's not the overall highest. But if we look just in its little neighborhood, it is the highest, so we call that a local maximum. Now let's look at this single minimum we have here. Is this minimum a local or global minimum? It is just local. The reason it's just local is because the ends of our graph are pointing down. So there are points that are lower than that minimum, but since the ends of our graph go on forever, right, with that arrow at the end tells us that graph is going on forever, there is no global minimum, because any point you choose on that end that's pointing down, there's always a point after that that's lower. Everybody kind of agree with that? So when we talk about extrema, the four types, we have global maximum, local maximum, global minimum, local minimum. Everybody's okay with that terminology? Again, these are things we talked about last year in your Algebra 3-4 course, so it shouldn't be any big surprise here. Is everybody cool with the vocab? Okay. The other key feature are the intercepts. So that's the points where the graph crosses the X or Y axes. So if I go and I look at the graph that I just drew above, I have a Y-intercept right here. And then I have several X-intercepts. Does everybody see the difference there between X and Y-intercept? Okay, so here's a question. For a polynomial, how many Y-intercepts can we have? Exactly one, right? For a polynomial function, you'll have exactly one Y-intercept. You cannot have 0. You cannot have more. How many X-intercepts can you have? Can you have 0? Yes. Yeah, think about a parabola that doesn't cross the x-axis, right?
Yeah.
You could have a parabola that doesn't cross the x-axis. We saw that last year. So you can have 0 x-intercepts. Can you have 1? Sure, right? Just any straight line, or any oblique line, I should say, something that's at like a diagonal, is going to cross the x-axis just once. That's a polynomial. Twice? Definitely. Like a quadratic that, where the u crosses twice. 3 times? 4 times? Okay. And you get the idea here, right? We can you build out your polynomial as big as you want. You can cross as many times as you want. There can be as many x-intercepts as you want. They don't necessarily have to cross, although you could have 0, right? You could have none. Everybody cool on that idea? The x-intercepts are sometimes also referred to as zeros. And the reason we say that is if I have the graph f of x or y equals f of x, my x-intercepts occur are the values of x that make y 0, right? So that's just like a little bit of vocab there for you. Let's talk about how we can use our calculator to find these values. So let's say we have x to the third minus x squared. Oops, I mean just minus x. Okay, let's say that's our graph. So I'm going to do zoom and then standard, so that I'm going to just graph that on the normal window from -10 to +10. Probably all of us would want to do zoom standard to graph this because we've been doing all those scatter plots in the previous chapter, so our windows, I'm sure, are all kind of cuckoo crazy right now. In addition, probably also a good idea is to make sure that your plots are all turned off before you try to do something like this. Again, if your plots were all on like they probably were from last chapter, and then though one of the lists is empty, you're going to get errors all over the place trying to graph something where it's like, hey, you're telling me to graph these points, but there's no points here for me to graph. Calculator hates that. You know what I mean? So just want to double check that. All right, so here's my picture. Now this probably isn't quite good enough to kind of see what's going on here. So I would probably readjust things. It looks like maybe if I go from like -3 to +3 and then -3 to +3, that'll probably be enough to kind of get a good picture of what's going on. While that zoom standard got my window back from cuckoo crazy to something normal, it still felt like I could get a little bit better picture there of what's going on. If I'm looking for intercepts and Extrema, helps a little bit to be able to see what's going on there. Does that everybody feel okay? Okay. All right, so now that I have my picture, let's go about finding, let's find the Extrema first. So I see I have what kind of maximum is this right here? Is this local or global?
Local.
Local. And then I have a minimum here. Which kind is this?
Local.
Okay. So to find a maximum or minimum, I'm going to be pressing the second button and then the trace command. If I look at this list of commands, which one sounds like the one I want if I'm looking for the that local maximum? Maximum command, yeah. Shocking. Whoa, boy. Pressed something wrong there. Can you come back over here, please? And I'm in a whole different set of notes. Cool. Maximum. So the calculator is going to ask me 3 questions. So it's going to ask me left bound, right bound, and then guess. So left bound, what it wants me to do is move my cursor on the left side of that maximum. So I'm just going to use my left arrow and move my cursor. Anywhere on the left side is fine. That's certainly to the left, so that looks good. When I've got my cursor where I want it, I press enter. It then is going to ask me for the right bound. So I'm going to just use my right arrow and move that cursor somewhere so it's on the right side of that maximum. And then I'll press enter. And then for a guess, it doesn't really matter since when we do this, we're only going to put one maximum in between our left bound and right bound. You can guess anywhere you want in between the left bound and right bound. So I don't even bother moving my cursor again. I just press enter again. So my maximum is at -0.577, comma 0.3849-ish. Is everybody cool with that? If I wanted the local minimum, we'd be doing that the same way, except instead of picking the maximum command from that second trace menu, we'll pick the minimum command. Calculator is going to ask me the same 3 questions, left bound, right bound, and guess. So I'll just move my cursor somewhere on the left side of that minimum, press enter. Somewhere on the right side, press enter. And then for the guess, just press enter where I'm at. So my minimum is at positive 0.577 and then negative 0.3849. Feel okay with what we did there? Okay. If I want the Y-intercept, I'm going to go and press second trace. This time I'm going to select the value command. So notice at the bottom of the screen, the calculator is asking me to input a value for x. What is the x coordinate always on a y-intercept? 0, right? So I just do that, and it says, oh, look, the y-intercept is at the point 0, 0. Shocking. As if I couldn't tell by looking at the picture. Sometimes it won't be so obvious, but everybody's cool with that? Okay. And then to get the X-intercepts, again, I'm going to be going to that menu, second trace. And this time, what do you suppose I'm going to pick for X-intercepts? Remember, what's that other term that we can use for X-intercepts? Zeros. So guess what I'm going to use? The 0 command. Wah, wah, wah. So the 0 command is going to ask the same 3 questions as usual, left bound, right bound, and guess. So let's say I'm going to look for this X-intercept first. So I'm going to just move my cursor on the left side of that guy. That looks like a good spot. I'll press enter. I'll move it somewhere to the right side of it, press enter, and then for my guess, I'll just press enter where I'm at. So one of my X-intercepts is negative 1, 0. Everybody okay there? And then I just repeat that process 2 more times to find the other 2 X-intercepts. Do you guys remember doing this last year? This was something you should have done in your Algebra 2 course last year also. Go back and get this. Okay. So let's do a little quick summary here. Okay. So we do maximum to find the maxima. We do minimum. That'll find the minima. We did value to find the y-intercept using 0 for x. And then 0 to find the x-intercepts. Is that helpful to just kind of re-summarize where the stuff is on the calculator there? How you use those things is pretty easy, but where they were at, probably helps. Okay. So the main focus, though, for this chapter is going to be looking at doing these sorts of things without the use of our calculator. So without just looking at the graph and using the calculator to find these things. Most of what we're going to be looking at is being able to figure out how to do this by hand with pencil and paper. But we can always kind of default and use these tools to kind of check our work and things. So what we're going to be spending the next several lessons doing is kind of building out the tools that we need to do this by hand, which we did last year in your Algebra 2 class, which hopefully these things will kind of ring some bells. And there's a little pieces here and there that are like, we'll go a little bit further than we did last year. But much of what we're going to do here is going to be the same techniques we used last year. So the first big piece, we have the following theorem, which is like the corollary to the fundamental theorem of algebra. You remember the fundamental theorem of algebra is that all polynomial equations are solvable depending on like what set of numbers we're solving over, whether it's, real numbers or complex numbers or whatever. The corollary to that says that a polynomial of degree n will have at most n zeros and n minus 1 extrema. So much of what we're going to be interested in is going to be finding the zeros for polynomials. And in order to do that, it's super helpful to know how many zeros we should be hunting for, right? Like, is this problem going to have 1, 2, 3, 4, 10? Like, how big of a problem is this? So let's say that we have the polynomial here, f of x equals 3x to the fourth minus 5x to the third plus 2x plus 2. What is the degree of this polynomial? What'd you say? 4. Yeah. Again, remember the degree of the polynomial is just the biggest exponent on our variable. So what this tells us is that there are at most 4 zeros and 3 extrema. Notice here it's saying at most. So that really means I could have 4, 3, 2, or 0 zeros. And I could have 3, 2, 1, or 0 extrema, right? Everybody's okay with that? We don't know for sure, but we know it can't be more than 4 zeros and it can't be more than 3 extrema. Now we're going to develop a lot of tools using or to find the zeros. We won't have so many tools. Come on now. So many tools to help us develop or to find these extrema, but there is some things that we can say about those extrema. One thing that we will be able to tell is if the extrema that are present could be local or global. And one way we can do that is describing or talking about the function's end behavior. And the end behavior of a function is just describing what the arrows on the graph are doing. So let's look at a fairly complicated example here. So if I look at this, how many arrows do I see on my graph here?
6.
Yeah. So we have 6 end behaviors to describe. Is everybody okay with that? So when we describe these end behaviors, we need to describe what's happening kind of to the x coordinate and what's happening to the y coordinate. So let's build out a little bit of notation to do that. And the notation we're going to use here is going to be more technical than what you did in your Algebra 2 class, but the idea is no different from what we've described before. Okay? So let's say the name of this graph is just f of x. And the notation that we're going to use for this is going to be called a limit notation. So what we're going to write is the letters LIM that are just short for limit. And underneath that, we're going to write x with an arrow. And we're going to say the limit of the function, in our case, our function is f of x, is going to equal. And then we're going to talk about what we're going to fill in to these 2 spots here in just a moment. But every time we describe an end behavior, it's going to look like this, except for what we're filling into those 2 places that I highlighted. Okay? So if I look at this first end behavior, what's happening to the x coordinate with that arrow? Is that x coordinate? It's getting infinitely small, right? Because the arrow's pointing to the left. And what's happening to its y coordinate, though? It's getting infinitely close to 0, right? Remember that dashed line is an asymptote? So the graph's going to come right up to that, but not cross it. So what we're going to fill in here to the x spot is a negative infinity, because the x coordinate was getting infinitely small. And what we're going to fill in to the equal spot is 0, because the y coordinate is getting infinitely close to 0. We're just going to finish up this idea, then we're going to be done for today. Just FYI. So this is like our last idea that we'll talk about. Okay? Let's look at the second end behavior there. So I'm going to write that part because that part's the same every single time. Now if I look at our second end behavior, I look at that arrow. What's happening to that arrow's x-coordinate? Oh, I guess we need a value here on this asymptote. Let's say that one's -2 and this one is +3. So the x-coordinate at that second end behavior is getting very close to what value? -2, right? Because it's coming right up to this line, -2. And what's happening to its y-coordinate? Right? Each time I'm getting a little bit closer to -2, what's happening to the y-coordinate? It's getting smaller and smaller. As they're going to keep getting smaller, the closer I get to -2, the smaller that y-coordinate's going to get. Everybody agree with that? So the limit is approaching the x-coordinate of -2, and the y-coordinate then would be -infinity because the arrow's pointing straight down. Is everybody okay with that? If I look at 3, what's going on here? What x-coordinate is that arrow heading towards? Well, we're talking about this spot here. So what x-coordinate? Still -2. And what y-coordinate? Since it's pointing straight up, +infinity. Exactly, yep. Okay, let's look at the second spot, or the spot number 4. Okay. What x-coordinate is that spot heading towards? Three. And what y-coordinate is that heading towards? -infinity, because it's just pointing straight down. Okay. Let's look at 5 now. What are we? What x-coordinate are we heading towards for 5? Well, that's the y.
Can you say that x is still 3?
It's still 3. That's correct. Absolutely. Is this feeling a little bit more comfortable as we're going? This is a really complicated example. far more complicated than you'd have to do, but I just wanted something where I got a lot of bang for our example buck here. So I wanted a lot of ones to do. All right, last arrow is here at 6. Is this being bounded at any way by an asymptote? Is there an asymptote right next to that arrow in any way? No. Great. So since that arrow is heading to the right, the x's are heading towards positive infinity. And because that arrow is also heading up, the y's are heading towards positive infinity. That feel okay there? All right. So if we look at a graph, fairly easy to do this, right? All we're doing is looking at a picture and kind of interpreting what we see and fitting it into the notation. What if instead of being given the picture, we're given the equation and we're asked to do this numerically? Well, first, what type of function do we notice here? What is this? It's a polynomial, right? Everybody agree with that? Okay. Can a polynomial have an asymptote? Never. So we know that there's only going to be 2 arrows on this graph. There's going to be an arrow at the left end and an arrow at the right end. Everybody okay with that? So the arrow at the left end, the x's have to be going towards negative infinity. And the arrow at the right end, the x's have to be going towards positive infinity. Is everybody okay with that notion? Okay. So what I'm going to do then is I'm going to go ahead and do a numeric test and look at what's going on with my function as the x's get very, very small and then as the x's get very, very big. So I'm going to go to the y equals menu and I'm just going to type in my function here. And I'm going to exit out to the main screen here. And I'm basically just going to do some test cases. So maybe like when x is negative 100, and then negative 1,000, and then maybe negative 10,000. And just kind of see what's happening. And we'll do the same thing here, but with positives. Right, because x is getting very, very big. I'm picking very big numbers. Here, x is getting very, very small, so I'm picking very, very small numbers. Are there anything magic about the numbers 100, 1,000, and 10,000? Nah. I just want numbers that are getting like a lot bigger or a lot smaller each time. Okay? So the easiest way to do this is then to just retrieve and use that y equals or y1 notation like we used in the previous chapter. So to retrieve the y1, I'm going to press the vars button. I'm going to go over to the y-vars menu. I'm going to pick the function option and select y1. And then I'm just going to do y1 of negative 100. So there's that value. And then rather than retrieving Y1 again through pressing all those buttons to go back through all those menus, if I press second and enter, it'll just put the last thing I typed in back on my calculator. And I can just go back and add an extra 0. What are we noticing is happening to the output here? It's getting smaller each time, right? So I start at negative like 2 million, and then I add negative, what's that, like 2 billion, and then negative 2 times 10 to the 12th. Woof! That's like 2 trillion or something, negative 2 trillion. So what we're seeing is that the function is getting smaller and smaller each time, right? So I know that it's getting progressively smaller. That means the arrow's pointing down. Right? As I go left, things are getting smaller. Means that arrow's pointing down. Does that feel okay? And now I can do the same thing with the positive. So I'll just go back and press the second and enter buttons to retrieve that and do a little editing. So I'm just doing Y1 of a 100 and do the same thing. So I have, I don't know, like 1 million something, almost 2 million there. Almost 2 trillion, or I'm sorry, billion. And then I do it again and I add another 0 and woof-a-doozies. I got a big boy there. But what I'm noticing is just that same kind of behavior where this time I'm getting bigger and bigger. Oops, wrote down the wrong one. They look so much alike. Yeah, just round that to 2 decimal places, I suppose. And since as I'm going and my x's are getting bigger and bigger and bigger, my y's are getting bigger and bigger and bigger, I know that arrow's kind of pointing up as I go to the right. Does that feel okay? So if I ask you to like support your answer numerically, I'd expect to kind of see 2 tables like this, right? Do the x values that you pick matter? Could have you done 7, 15,000, or negative 15,600 and like negative 10 million? Sure. Like it doesn't really matter. They just need to get like progressively, bigger or smaller, and make them bigger and smaller by a lot, like at least a factor of 10. But like, it doesn't matter that much.
So can we just use that 100?
Yeah, you could use those same 3 values every single time. Absolutely. And for polynomials, we only are ever going to have 2 arrows, and they're always going to be the left end and right end. So it's always could be those numbers for any polynomial. Okay, dokie. All right, I said we're going to stop here. We're going to stop right here. This feels like a good natural place to end.